Good afternoon, everyone. Welcome to Parsons Technical Webinar Series. I'm your host, Jessica Bennett. We're very excited for today's webinar that will be presented by Eleanor Jennings on the use of cutting-edge molecular microbial technologies to drive a successful, novel, enhanced bioremediation of legacy contaminants. Next slide, please. So just a few housekeeping items before we get started. We'll be keeping all phone lines muted until the end just to keep down background noise. If you have any questions throughout the presentation, feel free to submit them using the chat feature and we'll answer them at the end. When you do ask questions, please include your affiliation and your name so we know who's asking. And this webinar has been approved for 1 PDH credit. If you'd like to get a certificate for that, you can download the attendance form in the chat feature. If you're external or guest to this webinar, you may not be able to download it due to security restrictions. So please just email us and we'll get that to you. There are a few questions on the attendance form that you would multiple choice that you have to respond to. I'll post that in the chat as well for anyone who can't download the form during the webinar. And finally, this webinar is being recorded and will be posted on our YouTube channel in the coming days, where all of our prior webinars have been posted as well. So brief agenda, I'll introduce our guest speaker, Eleanor Jennings. She'll present a core value moment, and then she'll run through her presentation, and we'll wrap up with Q&A at the end. So Eleanor Jennings is a principal environmental microbiologist and biogeochemist at Parsons. She's also a subject matter expert and fellow. She's headed up bioremediation projects on multiple different continents and given over 125 presentations nationally and internationally on the topic. She also just recently concluded 9 years as the National Committee Chair and National Board Member at the American Society for Microbiology. She's an advisor to the Natural Sciences and Engineering Research Council of Canada, and she's also a co-author on a soon-to-be released ASTM standard on the use of molecular biological tools in environmental remediation, which will be tied to her presentation today. With that, I'll hand it over to Eleanor.
Thank you very much. You can hear me all right?
Yep, sounds good.
Okay, great. Thank you. Okay, so this is the part of our talk where I am supposed to pick one of the 6 Parsons core values, and I'm supposed to explain how this project actually highlights this particular core value. The reality is this particular project that I'm going to be talking about today actually hits on every one of the 6 Parsons core values. So we're going to actually be touching on those as we go through the talk itself. Before I go any further, I really, it's critical that I thank my project team. Without them, this project could not have happened. It certainly would not have been successful. And their help was just incredibly integral to the project. So I want to make sure that they get recognized. So let's just kind of jump head first in and let's address the elephant in the room, which basically is, why are we even still talking about benzene? I mean, we've known literally for decades that benzene can biodegrade quite well and quite successfully under aerobic conditions. We've known for decades that benzene can biodegrade quite well and quite successfully under all of the anaerobic conditions. So, you know, why are we still worried about it? You know, most of us who are bioremediation experts kind of, you know, we looked at the hydrocarbons, we were happy, and then we kind of started moving on to new classes of compounds. We moved on to dealing with the bioremediation of chlorinated compounds, munitions. Of course, our current favorite class of compounds are the PFAS compounds. But benzene always kind of remained a nagging issue at many sites. The reason for this is because of the other compounds often associated with benzene that will actually biodegrade preferentially to benzene. This has left us with sites that are unable to get regulatory closure because of the legacy benzene that still remains. And it's this benzene that is in fact our regulatory driver because regulators knew that other compounds would degrade preferentially to benzene. So these regulators decided to essentially monitor benzene with the assumption that if benzene has gone away, then the other compounds have gone away too. Well, this makes a lot of sense, but it leaves us dealing with a compound that we really thought we had conquered. And because of this, I almost think of benzene as sort of a re-emerging contaminant. And honestly, this is why we're still dealing with it. So our particular site, the site itself is built on part of a former factory town. And this factory town was really involved in brick manufacturing and also had a smelting facility associated with it. So this particular area we would think of as almost heavy industrial, and that's before this facility was built. The refinery was built and operations began in 1911. This facility produced liquefied petroleum gas, gasoline, fuel oil, and asphalt for approximately 70 years. In 1983, gasoline and heating oil production ceased, but the terminal was still definitely in use. As site activities slowed, decommissioning was initiated in a lot of different areas, though, of the facility. Hydrocarbons are definitely the primary contaminant throughout the facility. And in fact, in 2008, legacy benzene was actually named the primary regulatory driver for the facility. And this is just like we talked about, benzene is a conservative indicator due to its biodegradation potential in comparison to other hydrocarbons. And for our particular location, we were given a corrective measures implementation action level of 100 micrograms per liter. This particular facility is still currently an active petroleum products terminal. It's mostly decommissioned and dismantled, but it is still undergoing active remediation and restoration in a lot of different target areas. And this includes what I'm going to call Area of Concern, or AOCX. And AOCX is up here kind of in the northern part of the facility, up near sort of the northern side of it. AOCX is extremely heterogeneous, and this shouldn't be surprising. This facility, just like all of the facilities like it, you've got a long history of underground and above ground structures being built and then dismantled, and then new structures built and dismantled. You've got backfill going in, landfill material being used. So the fact that the subsurface is really heterogeneous shouldn't surprise anybody. But it is one of the more significant sources of remaining benzene at our facility. In 2013, an investigation was conducted to determine the best corrective measures for dealing with the residual benzene. And in 2013, in situ chemical oxidation, or ISCO, was actually proposed. So from 2013 into 2014, sodium persulfate-based ISCO injections were conducted, and this was followed by monitoring. But what they found in 2016 into 2018 is that dissolved benzene was being found above the CMI action level in 6 of the 12 monitoring wells that were associated within the former ISCO treatment area. And just to kind of give you some ranges, both TPH-GRO and TPH-GRO values, concentrations range from non-detect all the way up to 32,000 micrograms per liter. So we were stuck with a problem. And the problem is that this facility is a pretty high profile location. And it's got a very complex above ground and below ground infrastructure, just sort of as a result of its long history and uses. We're dealing with a shallow water table, and many of the areas are under strongly anaerobic conditions. Over the years, multiple conventional remedial actions were previously attempted, but the problem is that residual benzene has remained and is preventing regulatory closure of this AOC. Traditional remediation methods, really, we took a look at it, and they're just no longer technically feasible or cost effective for this area. So we needed to come up with something new. So we began looking for a solution, and the goal was to figure out a new way to effectively and efficiently reduce the mass of residual benzene, but we wanted to do it in a way that worked with the anaerobic site conditions. Sometimes remedial efforts take an anaerobic site and they try to make the site less reduced, even to the point of trying to push it into an aerobic situation. And we just didn't think that that was going to be feasible or effective at this location. We really wanted to work with the anaerobic condition. We also figured out that if it worked here, maybe we could apply it to other areas of the facility. So this AOCX kind of became a proving ground for us in some respects. So in 2019, we began a really in-depth biogeochemical assessment, basically trying to answer a couple of questions. And those were conditions favorable for an enhanced in situ bioremediation project, specifically under anaerobic conditions? And if yes, how would we go about doing it? So like all good projects, we came up with a plan. And our plan had 3 phases. And we're going to go through each one of these phases in chronological order, starting here with phase 1, where we targeted some representative monitoring wells within AOCX. We then collected, evaluated some detailed geochemical data, and we collected and evaluated detailed direct microbial data. So looking at the phase 1 assessments, what you'll see here is that we actually looked at sort of 3 categories, if you want to think about it. We have our contaminants of concern, we have the M&A parameters that we looked at. We also have a really nice suite of direct microbial assessments that we did. So for right now, and we will go through each one of these, and we're in particular going to be focusing on the microbial assessments. But for right now, let's focus only on the contaminants of concern and the M&A parameters. So for the contaminants of concern, we looked at VOCs plus ticks, as well as SVOC and ticks and metals. For the M&A parameters, we had some historic data, but it was really spotty. Certain areas at certain times had some of these parameters taken, but other areas had no data taken. So we actually wanted in 2019 to just start getting a really nice comprehensive suite of these geochemical parameters that we can indirectly look at the microbiology and kind of get a feel for what's going on. So looking at what we found and what the geochemistry told us in regards to the benzene, because that's really our focus for today. Benzene concentrations in AOCX range from 79 to 1800 micrograms per liter. The concentration trends did follow historic trends. So in other words, monitoring wells that traditionally had lower benzene concentrations, in 2019, they still had the lower concentrations for the area comparatively. Monitoring wells that were comparatively higher in benzene concentrations, in 2019, they were still higher in concentrations. But overall, in 2019, the concentrations of benzene that we found did tend to be lower, and they trended lower than what we found in the past. Looking at the M&A parameter data, again, we used available historic data as well as the comprehensive survey that we conducted in 2019. And the finding is that AOCX is definitely anaerobic. Areas with higher benzene concentrations tended to be dominated by mild to moderately sulfate reducing conditions. Areas with lower benzene concentrations tended to be dominated by more moderate iron reducing conditions. So definitely fell within what we had expected to find based on historic information. So now it's time to get into the fun stuff, or at least I consider it to be the fun stuff, and it's the microbiology of the site. We actually were able to do a really nice suite of microbial assessments. We looked at the community diversity of the indigenous microbial populations. We actually did a full metagenomic analysis looking at the full community members, both their composition and function. We also did a quantitative polymerase chain reaction, or QPCR, assessment to target and quantify a very specific organism, DELTAPROTEOBACTERIUM ORM2. And we also then finally did a stable isotope probe analysis. I'm going to go through each one of these step by step. But I just wanted to let you all know what the full suite of assessments were. So we're going to start with the metagenomic analyses. And if you're not really familiar with these are actually, they're extremely powerful because they look at the full microbial community in the tested environment. For us, it was groundwater, but they do so without pre-designed targets. A lot of you may have had projects where you wanted to know what is the population size of Halobacter, let's say, or what is how many gene copies per mil for a very specific gene involved in toluene biodegradation in your environment. So you may have done that before, but you're actually going and targeting very specific genes that can look at very specific functions or very specific populations. The metagenomic analyses go in without any pre-designed targets whatsoever. Instead, we did two things. The first thing we did is we looked at the full community composition. Basically, we're asking the question, who is there? Secondly, we're also looking at the relative size of each of the taxonomic groups. And then finally, for each of the taxonomic groups, what's their proportion to the whole community? The second assessment that we did looked at community function and really asked the questions, what activities are the full microbial communities doing? What is the relative size of each of these types of activities? And then what percentage of the total community is conducting which forms of either respiration or key environmental metabolic biodegradation functions? So basically, in general, who is there and what are they doing? That's what we went in to look at. And so for the first analysis, looking at who is there, what I just want you to look at, because there's a lot on here, and I know that, and you're probably like, wow, I can't read half of it. That's fine. I kind of don't want you focusing on that. The only thing you need to know is that here at the bottom, you've got each of the 5 samples that we ran. And then along the left side, you have, for this particular analysis, because we were looking at who is there, we have the either different classes of organisms that were identified or sometimes specific genera that were actually identified. And then within each individual sample, so we're going to use maybe the pink sample as our example. You'll see that the bubbles, some are smaller, some are larger. The size of the bubble is in proportion to the proportion of the total community. So in other words, the larger the bubble, this particular population is actually a Rhodophyrax genus. This had a pretty large proportion of the total community members for this particular sample. The second assessment that we did, again, was looking at what are they doing? And it's really the same type of data and presentation. You've got the 5 samples down below, and then along the side, what you have are the different activities. And the size of the bubble is mathematically representative of the size of the proportion of the population. So these 2 huge data sets with all of their bubbles, what does it mean? Well, starting with the first one, where we looked at the assessment of the full community composition. What we found was that anaerobic genera and species strongly dominated all samples, and that completely followed what we expected to see based on the geochemistry that we had at the time. Again, Rhodophyrax was a microbial genus that actually dominated most samples, which was kind of interesting because this is a benzene degrader that functions under iron-reducing conditions. So that actually pointed in a really good direction. It was like, great, we probably got active benzene degradation going on. But what we also found was a pretty wide range of population sizes between the different identified groups and genera. And this is a reflection of population diversity. And we actually had pretty good high levels of population diversity. And that's good because higher diversity in your microbial population can provide some level of resilience if environmental changes start to occur. But the nice thing is taken together, all of this data that we found from this particular assessment was in line, sort of pointing towards an anaerobic enhanced in situ biosolution. So going into the second metagenomic analysis, where we looked at full community functions, what we found was that iron-reducing and sulfate-reducing metabolisms were strongly present in all samples. And again, that totally fell in line with the geochemistry that we had. We actually found that what are considered to be general hydrocarbon biodegradation functions, these were found in all samples. And in particular, aromatic hydrocarbon biodegradation functions were present in multiple samples, up to just under 9% of the total population. So that's actually a pretty good piece of your population that's not just biodegrading hydrocarbons, but specifically going after aromatic hydrocarbons. So again, all of this data, it fell in line with the geochemistry that we had and it matched up. But more importantly for us, it started again pointing that an anaerobic enhanced in situ biosolution might actually work out here. So the next thing that we did was we did a quantitative polymerase chain reaction, or QPCR, looking at the organism DELTAPROTEOBACTERIUM ORM2. And this particular reaction, it does quantify your specific target. And the reason that we were targeting DELTAPROTEOBACTERIUM oil refinery microbe 2, which I'm not going to call it that ever again, I'm just going to say ORM2 because it's easier. The reason we were going after ORM2 is that this is an anaerobic benzene degrader that was originally isolated at a refinery in the US. And it's one of approximately only a dozen or so total anaerobic benzene degraders that's been fully characterized. We know a lot about the aerobic benzene degraders. We know that there are a lot of them, and we know how they work and function. The anaerobic ones, no, not so much. And so the fact that we know a lot about ORM2 and how it works is a big deal. Even bigger for our particular project is the fact that ORM2 biodegrades benzene quite happily under sulfate reducing conditions. And this organism was enriched originally in the laboratory of Dr. Elizabeth Edwards up at the University of Toronto. And it is part of a co-culture that's newly available for an enhanced in situ bio use. So when we actually ran our QPCRs for ORM2, all of our samples did report ORM2 to be present. So that was fantastic. The results were that ranged between 10 to the 5th and 10 to the 6th gene copies per liter. And just sort of for some perspective, 10 to the 3rd is about the lower detection limit for the analysis. 10 to the 7th to 10 to the 8th, that's kind of the population size see for just really great, really strong benzene biodegradation. You never really ever see numbers quite that high at a site like this unless you've already gone ahead and done an enhanced bio type project. But our numbers that we found, for the indigenous population size, they're actually pretty good. They're definitely there, and it's high enough that it was a pretty healthy population. So we were really excited about this. But it kind of then brought in a new question. And that new question is, well, how similar is the lab strain of ORM2 that we would be using for an enhanced in situ bio? How similar is that to our in situ isolates? So we actually went ahead and had the genetic sequences of the ORM2 lab strain compared to the isolates from the facility. And the results actually showed a really high degree of genetic similarity between the facility isolates and the laboratory strain. And this was fantastic. We were actually really surprised about this. This is excellent news for any potential bioaugmentation project, because that really high level of genetic similarity strongly suggests that the laboratory strain of ORM2 that we would be using in an enhanced in situ bioaugmentation injections would successfully survive and reproduce under facility environmental conditions. And last but not least, we did a stable isotope probe analysis, which is a commercially available in situ microbial sampler that a lot of you have probably worked with. We used it simply just to confirm that benzene biodegradation was occurring under in situ conditions through the use of isotopically labeled target compounds. So for this was benzene. And we did in fact confirm in all samples the presence of an active indigenous benzene biodegrading microbial population. And these were in the same monitoring wells as all of the previous analyses. And what we found in all monitoring wells was that the C13 isotopic tag was actually incorporated into the biomass. And for 2 of the 5 monitoring wells, we found that the C13 isotopic tag was found in trapped CO2. So what this actually means together is that the indigenous microbial population that was there is actively biodegrading benzene, and they're converting the carbons from that benzene into biomass. And in a lot of locations, they're actually also fully mineralizing it all the way down to CO2. So I know I've thrown a lot at you, so let's kind of take a step back and summarize where we are at this point. So for site geochemistry, The site is dominated by iron reducing to sulfate reducing conditions. And these are definitely conditions that are favorable for microbial biodegradation of benzene. We actually had some indirect geochemical evidence of M&A through looking at M&A geochemical parameters. And the data that we had from the site geochemistry, it really all pointed toward using anaerobic in situ bio, that this might really work. Looking at the microbiology data that we had obtained, we had conducted full member and full function metagenomic analyses, and were able to show there was a really diverse indigenous community that looked like it was going to strongly support anaerobic benzene biodegradation. We had the critical ORM2 microbe present in all samples, and this the indigenous ORM2 that we found at the facility was genetically similar to the in situ enhanced in situ bio co-culture strain that we were going to be going ahead and injecting. Benzene biodegradation under in situ conditions was confirmed through the use of stable isotopes. And again, all of this really pointed towards the idea that an anaerobic enhanced in situ biodegradation remedy would actually work and be successful out here. So that brought us to phase 2, which was great. We have all this data. Let's actually put it to use, and let's actually do a study, an implementation study on the ground. So this was actually initiated in March of 2020. And if you remember, things in the US got very interesting in March of 2020 due to the virus that we are all sick and tired of. I cannot tell you the location of our facility, but I can tell you that in March of 2020, this facility was in the absolute hot zone for COVID-19 here in the US. And so we were in a pretty sticky situation as to what was going to happen and how we were going to do things. The facility activities were determined to be essential by the state, and our particular project was deemed to be essential. So the first thing that we had to do was Parsons had to kind of step back and develop additional protocols in order to conduct work safely. And at the time, keep in mind, everybody was kind of making up the protocols as they went along and as we were learning about this virus. And so I really want to give a huge shout out to Melissa Layfield at Parsons, who helped us navigate clients' protocols, Parsons protocols, state, local, federal protocols, and the fact that all of these protocols were constantly shifting and changing. Melissa just did an amazing job, so I want to make sure she gets recognized for that. But we did get the go ahead. So we kind of figured out ways to do everything safely. And so Parsons went ahead and started constructing our injection system. And it was kind of cool the way we did this, because we actually found a lot of ways to reuse a lot of materials from other injection projects, either on facility or at other facilities. And so we were actually able to reuse a lot of materials when we built this injection system. The immediate goal for these injections were to enhance benzene biodegradation under sulfate reducing conditions. The long-term goals, however, were to learn how ORM2 was going to behave at the facility. Again, we were using AOCX basically as a testing ground for what we were doing. We wanted to learn how to maximize ORM2 effectiveness and efficiency, possibly because we wanted to then turn around and use this at other locations around the facility, or maybe at other locations. So the injections, these were actually conducted between March and June of 2020, and we did approximately 60 direct push locations. These were approximately 15 feet apart with a 3-foot radius of influence. Typically, these direct push injections were about 1 to 10 feet below surface. For the substrate injections, we injected the microbial culture containing ORM2, ferrous sulfate, sodium bicarb to maintain pH. And then we also had the material that we had to use to prepare the anaerobic water. And so we had a total substrate volume injected of just under 11,000 gallons. And so looking at our results, and this is just the results from inside the immediate in situ bio treatment area. And before we kind of jump into the data, just to point out that the blue line here that I'm trying to point to, this is actually the date of when, or the date range-ish that we did the enhanced in situ bio injections, so you know where those fall in regard to the history that you're looking at. The top red line, this is our corrective measures implementation action level, our CMI action level of 100 micrograms per liter. And the bottom red line, that's the groundwater quality standards for our facility, which is 1 microgram per liter. And so jumping into the data, what you're probably noticing is that things actually went pretty well at most of our sites, or most of the monitoring wells that we were using to monitor the injections. You know, we had the darker green line definitely went down. So we've got that now down below the CMI action level, as well as MP06R, the blue line. That and MP06R, the blue line, that's actually not just decreased to below the CMI action level, but that's actually decreased now to below our groundwater quality standards level, which is absolutely fantastic. What you're also probably noticing is the lighter green line up here, that's MW233. MW233 was kind of a head scratcher. We were trying to figure out why it did not show the excellent results that the other two wells showed. And when we went back into our records from the actual injection event, what we realized is that the area around there is a really, really tight formation, and they were having a really hard time actually injecting material into the subsurface. And there was daylighting. They just had a really tough time. And so without obviously planning it this way, what we ended up with is in the immediate treatment area through these 3 monitoring wells, we've got a really clear sort of comparison between wells where the material was successfully injected to the right levels, and we saw some great results when that happened. If the material doesn't get injected really well, your results aren't the best. So it kind of became kind of a control in some respects. And we're definitely, it's that challenge that you face at any site when you're doing injections, is when you've got that tight formation, how to really get stuff down in the ground. But when it does get down in the ground, it absolutely works. We've got some fantastic numbers. In MW33, this is the one with the tight formation area. We had daylighting issues, but even then, we still saw a benzene reduction from 330 down to 190 micrograms per liter. That's a 42.4% reduction in concentration. At MW350, we were able to reduce our benzene concentrations from 190 to 3.3 micrograms per liter. And that's a 98.2% reduction. And again, this is now, that's our current concentrations are now below CMI action levels. And so what that means for us is that no active remediation is required by the regulators. And we're actually approaching the regulatory groundwater quality standards, concentration of 1 microgram per liter. And then finally, MP06R. We've actually been able to reduce benzene concentrations there from 4,400 micrograms per liter down to 0.3, which is a 99.9% reduction. And fantastically, that's below our CMI action level and our regulatory groundwater quality standard level. So this kind of brings us here into phase 3. And this is where we're going to be considering implementation of this anaerobic enhanced in situ bio at other areas around the facility or maybe other sites. And that's actually currently where we're sitting at this point in time. So looking at the benefits of the particular project, we saw significant, we anticipate some significant long-term cost savings. Being able to get benzene concentrations to below CMI action levels, that's going to mean that we're no longer required to do any expensive active remediation, which is great. It's also, this really is proving itself to be a cost-effective solution to a problem that's preventing closure. And if we can get closure, that's going to be a huge cost savings, the faster we can do that. Although it's really innovative and it was custom designed, one of the benefits of this project is that we can absolutely adapt this to other facilities, either federal or private, and they can be done locations across the U.S. and the globe. The methodology itself can also be adapted to any environment or any contaminant. You know, not all project sites have the same needs. Not all project sites have the same questions that needs to be answered. And we know that it's important to customize the approach, but this methodology is definitely flexible enough that we can do that customization. And finally, the treatment and the protocols that were used have already been accepted by the key regulatory agencies involved. Going into the significance of the project, this is really the first time globally that this enhanced in situ microbial culture was used at a location such as this. There was a significant reduction in residual contaminant that was previously not able to be targeted for enhanced in situ bio. And we were able to achieve reductions below regulatory action levels, which is fantastic. We were able to address legacy benzene under highly anaerobic in situ conditions. And this is, you know, benzene is the subject of the regulatory driver at this location, as well as many other facilities and many other locations. So I promised you all that we would go into core values, and believe it or not, we actually have touched on all of them. In the core of the Parsons core value of innovation, this was a custom designed suite of biogeochemical analyses and very site-specific injection protocols that were designed. And it's really the first time that this technology was implemented at a location such as this. Looking at the Parsons core value of quality, there was up to a 99% reduction of a legacy contaminant that was preventing regulatory closure. In regard to the Parsons core value of diversity, we were able to utilize a really wide range of Parsons subject matter experts to provide the best possible work product possible. And we pulled subject matter experts from literally all across the country. And keeping in mind the timing of when this project was going on in relationship to the COVID-19 pandemic, these subject matter experts, we had to stay remote. We had no choice because we were under really strict travel restrictions, but we still managed to pull everybody together that we needed to get the job done. In regard to the core value of integrity, we followed a science-based stepwise approach to maximize project success. For the core value of sustainability, again, we were actually able to find some really creative ways to reuse materials when we were building the injection system, and we were actually to get a lot of cost savings from that. But it also is just, you know, anytime you can reuse something, that's definitely beneficial for a lot of reasons. And the last core value is safety. And again, I just cannot say enough about my project team for this. I am extremely proud of them and what they pulled off. By the time this project had concluded, we were happily able to report 0 injuries, 0 incidences, and 0 illnesses. And this, again, was all going on in the COVID hot zone in 2020. And we actually did such a great job. And again, I want to shout out from Melissa Langfield for all of her help try to coordinate the safety protocols. But we were actually invited to write up not just what we did, but the lessons learned from it. And we were invited to write it up in a technical journal and publish it. And so that then brings me to, if anybody has any questions, I'd be happy to answer them.
Thanks, Eleanor. That was a really fascinating presentation on how we can, you know, approach bioremediation and utilize, you know, conditions already at sites in a really novel way. So yeah, if anybody has any questions, feel free to, you can raise your hand and I can unmute you, or you can enter it into the chat and we'll read it out. So we have a bunch of questions in the chat, starting with Yong Li, after injection, what changes were observed for other chemicals aside from benzene? For example, toluene, ethylbenzene, and xylene, which may be chemicals of concern at different sites.
You know, we actually, I'd have to go back and double check the data, but if I remember correctly, we didn't see too many changes. Keep in mind, I mean, we think we saw some degradation. You're always going to get, I mean, the indigenous microbial cultures or populations that are down on the subsurface probably were happy to get an influx of sulfate and maybe took off with that and tried to use that to biodegrade the other BTEX compounds. But where we really saw the biggest impact was benzene, because that's the culture that we injected along with everything. So yeah, we did see some reduction in those chemicals. I'd have to go back to actually figure out the exact numbers and things like that. But there was reduction, but obviously the biggest reduction that we found was benzene.
Okay, great. From Cami Sra, you mentioned that ferrous sulfate was added along with degraders. What was the purpose of the salt? And in the presence of multiple amendments, sulfate, degraders, etc., what is the change in benzene really attributed to?
I mean, it's you know, the purpose of the ferrous sulfate was to get the sulfate down in the ground, keeping in mind that ORM2, it is a benzene degrader, but it definitely prefers iron reducing and definitely preferentially prefers sulfate reducing conditions. So we wanted to make sure, in addition to the actual organisms, we wanted to supplement it because it's not just, they just don't need the benzene alone. You need to have those supplemental electron acceptors, things like that, to actually help promote that metabolism. So that was the purpose of injecting the ferrous sulfate. And what was the second part of that question, please?
The second part was, in the presence of multiple amendments, sulfate, degraders, etc., what's the change in benzene really attributed to?
It's you know, both. I mean, I think that, you know, what we saw was we absolutely did inject the degraders that specifically do target benzene. We also injected material to help promote the ORM2 metabolisms. Like I said, I'm sure that the other indigenous microbes may have, you know, snagged on to some of that injected ferrous sulfate and used it, which is fine. We're happy. Anybody who's going to degrade it, we're happy to promote that. So, but you know, we definitely are attributing it really to the ORM2 injections, coupled with the fact that we were supplementing them with the right electron acceptors to do the job.
Okay, the next question is from Claudia Willicott Hutchinson. She said, you mentioned that this process and methodology can be modified to other contaminants. Can you elaborate a little more?
Yeah, I mean, definitely, you know, ORM2, if you have a contaminant other than benzene, ORM2 is not going to be the organism you're going to want to inject. ORM2 is very specifically going to be used to target benzene, but there are other commercially available cultures out there that we can use to target other compounds, you know, but just what we learned about the actual initial process of the biogeochemical analysis. So, you know, I think a lot of people, in what I've noticed, is they tend to just jump in and they want to start injecting things into the ground. I am personally somebody who's kind of like, let's take a step back. Let's see what's actually in the ground to start with. Let's see what current baseline situations and conditions actually are, and not just from a geochemical standpoint. So not just from your contaminants, not just from your M&A parameters, but let's actually look at the appropriate microbiology. You know, we went in for this particular study and we didn't have any prior information about the indigenous microbial communities. And we decided that the full function, full community metagenomic analysis really was the way to go. At other sites, maybe you have some other information historically. So we don't need to do that analysis. Maybe instead we can ask other specific questions that other molecular analyses are better targeting. But it's this idea or this methodology of kind of stopping, and instead of just jumping into the injections, let's really figure out what your current site conditions are. Let's figure out what the contamination concentrations really are and where they are. Let's figure out from the M&A parameters what's happening and what's available. And then from a microbiology, let's look at the appropriate microbiology for your particular target compound. Again, for us, it was benzene. So we knew we had anaerobic conditions. So ORM2 was the appropriate organism to really start looking at. But we also wanted to get a full community profile. At a different site, maybe with a different contaminant, we would take, we would just basically use different molecular analyses. But the overall process is definitely going to be the same. It's kind of the particular individual analyses. That's where we can start customizing it and tweaking it for the location, for the known information that's already out there, and for the particular contaminant that we're trying to target.
Okay, next question we have, we're getting some similar questions on that side, but I think that addresses several of them. So from Audrey Sidebottom, is this applicable only up to a certain max concentration? For example, M&A dissolve phase, but not necessarily natural source zone depletion?
That's a really great question. And that's actually a question I have had. We know for a fact, I mean, there's this idea out there that microbiology and indigenous microbes are only going to go after dissolved phase material, not LNAPL. And that's not really true. We know for a fact that LNAPL can be biodegraded. It's happening at the interface between the LNAPL and water. And it's obviously going to be pretty slow, and you're not going to see the fast results that you do in the dissolve phase. So we know that biodegradation can occur all the way up to LNAPL concentrations. Now, specifically looking at benzene and specifically looking at how much this specific organism, how much ORM2 can tolerate and handle and degrade in a certain time frame, we are still trying to figure that out, actually. I mean, this is a really, really, really new culture to be able to work with. I think at the time that we injected, I believe there was maybe one other location in the United States that injected it before us, and it was a different type of location and a different type of facility. And they only beat us by like 8 weeks. So this is a really new bioenhancement culture that we get to work with. So we're still learning that. So it's a great question. And it's one we're definitely asking ourselves. So, as far as natural source zone depletion, everything I've learned about the organism, everything that I've seen how it behaves in this particular study would suggest that we might be able to actually really go after source zone depletion using enhanced bio with ORM2. Everything's pointing in that direction, but I definitely think that that's something we would need to look at. So if we've got a site where we've got, source material and we want to go after source zone depletion, I say let's try it.
Okay, next question is from Karen Fields. How familiar were the regulators with this treatment approach before you started, and how receptive were they for using it at this site?
They were, the regulators in general are getting a lot better than they were even 5 years ago. They're getting much more familiar with the molecular technologies. As publications have come out, EPA themselves have published on this. John Wilson has been a really strong advocate for using these technologies responsibly and correctly. He's also been a very strong advocate for understanding their limitations, which is incredibly important. You don't want to be in a situation where you just overpromise and say it's going to do a great job and it's going to answer every question out there. No technologies, none of these technologies will do that. That's why you have to kind of look at your site, decide what your true questions are, and then you kind of custom design your geochemical analyses that you want to run. You custom design the molecular microbial analyses that you want to run. But they are more familiar with them and they're more confident and comfortable with them. I think for this particular site, if I remember, there were definitely questions in regards to using ORM2 because it's just so new, and they had questions about it. But that's when you just sit down with your regulator. This goes back to having a good relationship with your regulator and why that's so important. You sit down with them, you give them the information, you present it to them clearly, you tell them the benefits, you tell them the limitations, you tell them what you know and what you don't know. You be very open about this. But when you explain all the evidence that points into the direction that, number one, it's going to be safe, because obviously, it's kind of, I personally take the, I kind of steal from the medical doctors and their Hippocratic oath, where I say first do no harm. I kind of steal that when I deal with environmental projects. When you convince them that, you're not going to do any harm, and then you explain all the lines of evidence that show that, this has a really good chance of working and being successful, they get to be more comfortable with it. And we were also very upfront with the regulators, telling them that this really was, it was a new technology. Everything suggested that it would work, but we needed some basically pilot studies, and we needed to have an area that we could use as a proving ground to really see how things would behave. And they were okay with that. We just kind of had to really communicate well with them.
Okay, so from Ada Wong, how long did you conduct the performance monitoring, and how long after injection were you able to see the benzene concentration decrease in the field?
So we are still actually monitoring this site. So we did our injections in early 2020. So, we're still definitely monitoring it. And the results were actually, we could see them pretty clearly. And I'm actually going to go and I'm going to see if I can scroll back. There we go. Hopefully you guys can see this. So you can actually see the point in time marked here by the vertical blue line when we were doing our enhanced in situ bioinjections. And you can see that particularly in MP06R, the blue, and then in MP350, you can see that we were starting to get really positive responses really within the first monitoring period. So that was maybe like September of 2020, so 5 months later. But like I said, we are still monitoring all of these areas today.
Okay. From Doug Gray, did you do follow-up microbial analyses to track changes in populations post-treatment compared to the baseline conditions that you outlined in the presentation?
That's definitely in the works, and that's where you're working both with the client and the regulators, but that's definitely in the works. But the data that we presented, we had to kind of cut it off at a certain point in time, but hopefully that can happen and you will see a follow-up presentation.
Okay, so I know you just said the principles do no harm, but a question from Yong Lee is, are there any side effects of concern, such as elevated sulfate or sodium concentrations?
There definitely there could be, but that's where you have to really sit down in advance of injecting anything, and you have to that's where I step in, and it's first, let's stop, and before we inject anything, let's actually get a really good profile of the appropriate geochemistry of the subsurface, so we know how much sulfate is there, we know how much iron is there. Let's know what's there before we even consider injecting anything. And you design your injected material accordingly, both concentration and the actual type of material that you decide to use.
Okay, if there's any other questions, please feel free to raise your hand, or you can enter it in the chat. I think this one's maybe more of a comment than a question, but from Ravi Koldkar. It's so great to see efforts to leverage anaerobic biodegradation, which is prevalent at these sites, to enhance rate of cleanup. Perhaps we should continue discussing what's the most efficient approach to do so: bioaugmentation or biostimulation.
Yeah, no, definitely. And I think part of that, Ravi, is it may be site specific. A lot of this is how it worked here at this particular AOC at this particular facility, and this is the results. These are the results that we got. But at a different facility, and you know what, even a different AOC within the same facility, we may take a little bit different approach. We may have to tweak it and customize it a little bit. So you're absolutely correct. Sometimes, you have to switch the approach around. For this, this particular AOC, like I said, we really kind of wanted to use it kind of as a proving ground. We knew we weren't going to hurt anything. But if what we wanted to do, and if this enhanced in situ bio worked, that then meant that maybe this is another tool in our toolbox. It's another option that's available to use at a different AOC on this facility, or it's an option that we can maybe use at a different facility altogether. But because it was so new, we just kind of needed some proving grounds for it. And that's what our goal was for here. But I definitely take your comment to heart, and it's definitely true. You really have to look at each individual situation and really decide what the best approach is before you just start jumping in and injecting things into the ground.
Okay, we got a question. Are there any concerns with hydrogen sulfide generation?
We were looking at hydrogen. I'm sorry, go ahead. Or were you trying to finish something up, Jessica?
No, that wasn't me. I'm not sure what you might have heard.
Okay, sorry. No, I mean, anytime you're going to be dealing with sulfate, you kind of want to make sure you're watching your hydrogen sulfide levels, because those can be problematic at times. You do have to watch it. And again, it kind of just keeps rolling back to this idea of don't just jump in and start injecting material. First thing is, I can't stress this enough. Understand your true baseline chemistry and conditions before you inject anything. And then when you understand your baseline conditions, really think about what you're injecting and how much you're injecting. If you're injecting it pretty much all at one time, or are you going to space out your injections? I mean, are you going to hit it really hard and walk away? Or are you going to kind of take a low, slow method? We're going to do injections and then come back a month later and do some more injections, and then come back a month later and do some more injections. You really have to think about your site and really have a good understanding of your site, a good site conceptual model, good baseline data, in order to really make those assessments. But yes, hydrogen sulfide is always going to be a concern. We have been watching it here. I didn't present any of the data. So far, we have not run into any problems whatsoever. But yeah, you definitely do want to watch that, because obviously that's a safety concern.
Okay, well, that was a very active and I think engaging set of questions from the audience. So thank you to everybody who submitted a question. If we can go to the next slide. So hopefully everyone could download the PDH form. If you couldn't and you wanted to get PDH credit, please send an email to either daniela.savin@parsons.com or myself, and we'll get you that form. Our next webinar will be on July 13th at 12:30 p.m. Presented by Glenn Ulrich and Ron Krawcheck on risk-based and biotechnology alternatives to address natural gas emissions from leaking oil and gas wells and other methane sources, which should be a really kind of unique and novel presentation that we hope everyone can join us for. So again, thank you to everybody who joined us today for our webinar. We hope to see you again next month, and this webinar will be posted shortly in the next few days on our YouTube channel.